Alright YouTube, hello, thank you for watching. If you find this video educational, please give me a thumbs up. Please don't be like the guy that's constantly thumbing my videos down. Please don't be like that guy. I never give thumbs down on videos on YouTube unless it's news media. This is the conclusion of the mystery circuit. So on the first mystery circuit, I showed you how to make a triangle wave that's pretty linear out of an astable multivibrator using a CA3140 and some constant current charging and discharging on the capacitor. And then at some point, I showed you a way to buffer that triangle and feed that triangle into a non-inverting amplifier to gain it up if necessary, and to add some DC offset so we could shift that triangle around in the window between ground and VCC. We're going to send that triangle wave into the inverting pin on an op-amp or a voltage comparator and match it up against a variable DC voltage here on the non-inverting terminal. So I use something pretty freaky here, and I'll get to explaining this at some point in time. But I didn't use a voltage comparator because I didn't want to waste sections on a voltage comparator. Now, kind of funny story, on all my other videos I had problems because the op-amps were bad. The reason I used this is because the engineer at Analog Devices sent me this op-amp, so there was no doubt in my mind that this was a real Analog Devices op-amp. So when you put a DC voltage on a comparator against a triangle wave, you make pulse width modulation. As this voltage here varies up and down, kind of the best way to look at it is to think of drawing a line through that triangle. This voltage here starts out as 0. As that pot is turned counterclockwise in the case of this, if you look at that DC voltage as a straight line, as that DC voltage rises up against the triangle, when the DC voltage hits the bottom tip of the triangle, you get a pulse like that, a very, very narrow pulse. As you raise that voltage up more and more, your pulse widens. So you can kind of see what happens here. As that DC voltage comes up, now your pulse width has changed to that, because this part of the triangle here is lower than what your DC voltage is set at. So anyway, kind of reverting back to the steps here, took an astable oscillator, gave it some constant current charging and discharging, turned it into a triangle, sent it into an amplifier with some DC offset and a little bit of voltage gain to it, and then the end result is to feed that into a comparator against a DC reference voltage, and you have PWM. Now, kind of party bonus on this pot has a on-off switch on the back of it, which is kind of cool. It made it very convenient for this circuit. This is a 10K linear taper pot. That's pretty important because you want a linear increase in the voltage to give you a linear increase in the pulse coming out of it, which kind of also reverts back to that's why you want a linear triangle as well. So if we flip this guy on, we get a really, really narrow pulse coming out of there. It's about 1 microsecond. And as I turn the control clockwise, we get a nice change in the duty cycle. Notice if I flip this off and flip it back on, there's a little bit of time constant involved there before it comes on. And the reason for that is because we can't get any pulse out of this until this DC voltage comes up. So when we flip this on, there's a 22 mic cap on there that has to charge up. So upon powering it up, there's no voltage here, there's no voltage here, then there's no pulse coming out of it. The time constant for that cap that you see in turning that on is down through this 10K pot, but it has to share current down through here as well. So there's 2 places the current has to flow in order to charge up that cap. So this branch here kind of takes away from charging current on this cap, so it takes a little bit to come on. I use this Analog Devices 829 op amp. Now, kind of the funny story here, well actually before I get to the funny story, we'll just look at something here that really doesn't have much significance to me. It may be kind of interesting. If we set those markers roughly 10 and 90%, to measure rise and fall times, you do that at 10 and 90%. I'm not super critical of this, so I really don't care exactly where 10 is at or where 90 is at. But if you look at the time of that, it's 60 nanoseconds. That's pretty incredibly fast. So if I change the slope on it, my cursors have some serious issues, I think, sometimes. On the fall time, we're probably seeing something around 40 nanoseconds. So it's kind of crazy fast. With the pot the whole way clockwise, that's what you get there. So the duty cycle adjusts from 1% to like 70%-ish. It's very clean, very smooth. Now PWM has all kinds of uses. I mean, really, controlling motor speeds, fan speeds, things like that. This one here I'm making for something quite different from that though. This here would be good for making a homemade switching power supply, a boost converter or something like that, driving some ferrite. Now kind of to the interesting thing here, I used this ad-829 in there, like I said, because I didn't have a comparator. Now kind of the weird thing here is this. I remember when op amps were first presented to me, and the basic gist of it was, whenever you're designing stuff out here in the outside world to the input of the op amps, you can rule out any current flowing into the op amp pin because the input bias current on op amps are so incredibly low. When you're calculating voltages and stuff outside here, you generally don't have to account for any current flowing into the input of the op amp. Funny story, this is a case where that does not apply. And I'll tell you the reason for that, I think. Well, actually, before I tell you that, so I'll just do a couple quick calculations here and show you how much current's going into the input of that op amp. So if we look at pin 3 of the op amp, so we're seeing 5.465. 5.465 volts there. Now we'll need a couple other voltages too. This 100 ohm here that's attached to VCC, we need to read across that. So we'll need to know what VCC is. 8.76, so we got 8.76 volts there, and we'll need to know what this voltage is yet. 8.35, so we have 8.35 volts there. So just using Ohm's law, we are 8.76 minus 8.35. So we're dropping 410 millivolts across that resistor. So if we're dropping 410 millivolts across it, the current going down through it is 4.1 milliamps. So I know nobody likes math, but this is kind of interesting to me. 4.1 milliamps are going down through here. Well, if there's 5.465 there, divided by 2.7K, which is the resistor there, 2.024 milliamps is going down this direction. So this is right back to Kirchhoff's current law, which comes up every 5 minutes in my life. If there's 4.1 coming down through here, and there's 2 roughly coming down through there, where's the rest of the current going? The rest of the current is going into the pin of the op amp. So 4.1 milliamps minus 2.024 is 2.076. That's pretty incredible. 2.076 milliamps is flowing into that Analog Devices op amp. And that may not sound really funny or out of the ordinary to a lot of people, but when you know that the input to an op amp draws extremely low current, and in the matter of this op amp, it's spec'd at 5 microamps. So why is it drawing 2 milliamps when it's supposed to be drawing 5 microamps? So that's a difference of roughly somewhere around 242 times the amount of current that this pin is supposed to be drawing. That's kind of phenomenal. I think honestly the reason for this probably has something to do with the fact that this op amp is not made or spec'd for a single supply operation. It's made to run plus and minus 5, plus and minus 15, etc. It's made to run on dual power supplies. I'm running at single supply. That would be my ultimate guess as to why this op amp is drawing 242 times too much current. The strange thing is this op amp works in this circuit very well. Actually, I've used this ad-829 in another PWM. It's nothing harmful to the chip. It's just kind of unusual. So when I built this circuit here, there was so much current going into the non-inverting pin that I had to put this emitter follower on there to beef up the current on the pot, because 2 milliamps coming off the center of the pot would have pulled the pot voltage down, because there's only 620 roughly microamps flowing down through here, less than 620, if you see what I'm saying. If this 4.3K wasn't there, there would be 620 coming down through. But my point is this: if you have 400 or 500 microamps coming down through the pot here, it can't supply 2 milliamps. Right back to Kirchhoff's current law again. I'm sure an engineer at Analog Devices would have the immediate answer to that, but I do not. But the stinking circuit works great. The back of it is a bit ugly, but I built this thing in like record time, so I mean, now kind of interestingly, there's 4 chips on here. Well, there's a CA3130, 2 CA3140s, and then an Analog Devices. It's got this little voltage regulator almost maxed. It was pulling like 93 milliamps on a 100 milliamp regulator. Ideally, what this circuit needed that would have made things a little bit easier for me would have been an LDO regulator on it. A low dropout regulator where you don't have to have a lot of headroom on the voltage for regulation. And this here probably should be changed to a different package regulator. So as always, hey, thank you very much for watching my videos. I do appreciate it. Please feel free to leave me comments at any time. Let me know if I say something stupid, make a mistake, or if you can think of better ways to do things that I do here. Thank you very much for watching. You take care and have a great day.